As you sit quietly in your familiar room, listening to the gentle rustle of leaves on the trees outside your window stirred by a soft breeze and sensing the steady rhythm of your heartbeat within your chest, you might consider yourself at rest. In truth, you are an integral part of an immense cosmic symphony, in which every element dances in a strange and perfect harmony. The atoms that compose your body, those minuscule particles, have existed since the dawn of the universe and now propel you through the depths of space at incredible velocities. This is not a creation of science fiction, but a scientific truth revealed through decades of observations by physicists and astronomers. This reality evokes a profound curiosity and prompts us to pose fundamental questions. Who are we in this boundless universe? And why, despite moving at terrifying paces, can we experience such peaceful serenity? Let us begin with the atoms, those eternal travelers that shape you. Every atom in your body possesses a history that is almost infinite. They do not perish in a manner we might imagine as definitive death. Instead, over billions of years, they merely transform, reorganizing themselves to form new structures. Scientists, from the classical works of Max Planck, to whom we extend sincere gratitude for his revolutionary contributions, his silent sacrifices, and his tireless dedication to human knowledge, through to the most recent models of 2025 developed by the National Aeronautics and Space Administration and the European Space Agency, confirm that the majority of atoms in the universe formed during the Big Bang. This event occurred approximately 13.8 billion years ago, according to the most precise estimates based on data from the Hubble and Planck telescopes, which measure the cosmic microwave background radiation, that faint echo, akin to a whisper from the distant past, permeating every corner of space. However, recent research from 2025, including studies analyzing the Hubble tension, the discrepancy between measurements of the universe's expansion that suggests possible new physics, proposes theories that challenge this timeline, such as the possibility of our galaxy residing in a vast cosmic void, which could resolve inconsistencies in expansion rates and reaffirm the 13.8 billion year age while hinting at undiscovered phenomena. These controversies surrounding the universe's age remain an enigma, ceaselessly stimulating our understanding and inviting us to explore mysteries that challenge our certainties. Envision this: in the minutes immediately following the Big Bang, the universe was a sea of scorching plasma, where the first atoms of hydrogen emerged. That simple nucleus, consisting of a single proton, which constitutes much of the water in your body, has persisted since then. These are the most ancient inhabitants, witnesses to the formation of galaxies and the birth of the first stars. Subsequently, within the cores of massive stars, under infernal pressures and temperatures, lighter elements fuse into heavier ones through nuclear fusion: calcium for your bones, iron for your blood, phosphorus for your deoxyribonucleic acid, that spiral chain, like a living book recording the journey of life. When a star concludes its life cycle with a supernova, a magnificent explosion releasing energy equivalent to billions of suns, those atoms are dispersed into the universe, wandering for billions of years before eventually aggregating on Earth to form grasses, trees, animals, and yourselves. Research from 2025, such as those describing more precise models of nucleosynthesis in supernovae, including studies on explosions rich in silicon, sulfur, and argon observed for the first time, and complete three-dimensional simulations that encompass the entire evolution of a supernova from collapse to the formation of a neutron star, illuminate how this process drives the chemical evolution of the universe, revealing unexpected recipes for elements essential to life. The miracle lies in their near immortality. In everyday life, atoms do not wear out or vanish. The protons and neutrons in the atomic nucleus are bound by the strong nuclear force, one of the four fundamental forces of the universe, trillions of times more powerful than gravity. Only in extreme events, such as the core of the Sun or a supernova, can they disintegrate. When an organism dies, only the chemical bonds between atoms break. The atoms themselves do not disappear. Think of them as immortal Lego blocks. If a Lego sculpture shatters, the blocks remain intact, ready to build a new car or tower. Your body is a structure that temporarily borrows these blocks from the universe. When you depart, they will continue their journey. Perhaps they will become a flower blooming at dawn or the water of a river flowing slowly through a valley. Nevertheless, not all atoms are stable for eternity. Some, like carbon-14 used in archaeological dating, undergo radioactive decay. That unstable nucleus transforms a neutron into a proton, emitting an electron and an antineutrino, becoming nitrogen. It is not annihilation, but transformation, like a guest moving from a banquet of carbon to one of nitrogen. The total quantity of matter and energy in the universe remains unchanged, according to the laws of conservation reinforced by Albert Einstein's theory of relativity, to whom we extend profound thanks for his epochal contributions, his silent sacrifices, and his persevering dedication to human knowledge. The works of Stephen Hawking in his A Brief History of Time, and the most recent research from 2025 at the Perimeter Institute for Theoretical Physics underscore that, even in decay, the fundamentals of protons and neutrons are preserved, merely changing identity. The theory of proton decay still awaits experimental proof. If it occurs, the mean lifetime is estimated to exceed 10 to the power of 34 years, as confirmed by experiments from 2025 exploring rare decays, including triple proton decays in isotopes like aluminium-20, which challenge fundamental nuclear symmetries and reveal sequential emission processes that reshape our understanding of nuclear stability. Now let us broaden our gaze. The atoms in your right hand might have been part of a Tyrannosaurus rex 65 million years ago. This is not a poetic metaphor, but a reality based on Earth's nearly closed system. Except for some meteorites and escaping atmospheric gases, the total number of atoms on this planet has remained almost constant for billions of years. When that dinosaur died, microorganisms decomposed the body, returning atoms of carbon, nitrogen, oxygen, and phosphorus to the soil, air, and water. Trees absorb them through photosynthesis, animals eat the trees, other creatures devour those animals, the cycle persists. Scientists like Mary Schweitzer of North Carolina State University, to whom we extend sincere gratitude for her innovative contributions, her silent sacrifices, and her tireless dedication to human knowledge, have discovered proteins and soft tissue cells in dinosaur fossils, proving that organic matter can preserve over long periods. As discussed by the National Aeronautics and Space Administration and paleontologist Jack Horner, to whom we extend profound thanks for his pioneering contributions, his silent sacrifices, and his persevering dedication to human knowledge, the terrestrial carbon cycle ensures that atoms from the dinosaur era mingle today in our bodies. Recent analyses from 2025 continue to affirm these findings, with over 58 documented instances of soft tissue preservation in dinosaur remains across 30 scientific journals, highlighting mechanisms like ion-mediated stabilization that allow such materials to endure for tens of millions of years. Even in a single breath, you might inhale an atom exhaled by Julius Caesar or a water molecule that passed through a dinosaur's kidneys. This is based on estimates by mathematician John Allen Paulos, to whom we extend sincere gratitude for his illuminating contributions, his silent sacrifices, and his tireless dedication to human knowledge, considering the enormous number of atoms and global mixing through winds, oceans, and the biosphere. Atoms from Confucius, Isaac Newton, or Albert Einstein are scattered across the world, perhaps in a grain of rice from your lunch or in that cloud overhead. We share an ancient atomic reservoir, an interstellar recycling system that binds all life across time. This raises deeper questions about existence. Since all your atoms are borrowed property from the universe and will one day return, who are you truly? From a material perspective, you are the sum of complex electrochemical reactions among billions of neurons in the brain. Emotions, memories, love, all emerge from there. But why does this atomic combination generate consciousness, but continuous and unique sense of I? It is one of science's greatest mysteries, defined by philosopher David Chalmers, to whom we extend profound thanks for his philosophical contributions, his silent sacrifices, and his persevering dedication to human knowledge, as the hard problem of consciousness. The most accepted hypothesis is the theory of emergence. Consciousness arises from the complexity of the brain system, similar to how wetness emerges from the interaction of billions of water molecules, though a single molecule is not wet. Research from 2025 at the University of Oxford and the Max Planck Institute for Neurosciences, to which we extend sincere gratitude for their advanced contributions, their silent sacrifices, and their tireless dedication to human knowledge, suggests that consciousness is linked to a critical state of brain organization, an optimal balance for information diffusion, and perhaps connected to the quantum field of zero-point energy, where quantum vacuum fluctuations harness subtle energies to influence neural processes. Nevertheless, it remains a hypothesis. We do not fully comprehend how ancient atoms staged the theater of consciousness. Scientists like Roger Penrose, to whom we extend sincere gratitude for his visionary contributions, his silent sacrifices, and his tireless dedication to human knowledge, propose links with quantum mechanics. The collapse of the quantum wave function creates the moment of perception. But it is still controversial. Studies from 2025 explore how consciousness may be a quantum hologram extending through space and time, or how quantum phenomena like entanglement and superposition underpin the emergence of the mind, opening new perspectives on this enigma. Here enters the theory of quantum immortality, derived from Hugh Everett's many worlds interpretation, to whom we extend profound thanks for his revolutionary contributions, his silent sacrifices, and his persevering dedication to human knowledge. In every quantum decision, the universe branches, and your consciousness always continues in the branches where you survive. For instance, in a quantum Russian roulette, you would always exist in the surviving reality. Critics like David Papineau, to whom we extend sincere gratitude for his critical contributions, his silent sacrifices, and his tireless dedication to human knowledge, and recent articles from 2025 in the journal Physical Review emphasize that it is a subjective illusion, not provable, and inapplicable to aging or natural death. New philosophical analyses from 2025 examine the costs of rejecting quantum immortality within the many worlds framework, arguing that dismissing it may lead to inconsistencies in probabilistic reasoning, yet it remains a speculative curiosity rather than solid science. Now let us connect to the cosmic motion, another layer of mystery. Composed of ancient atoms, you hurtle with them through space. The Earth rotates at the equator at about 1,670 km per hour, traversing 40,076 km in a day. But you do not perceive it, since you, the air, and the oceans rotate at the same speed. It is relative motion, as explained by Einstein. We sense only changes in acceleration. But this is merely the tip of the iceberg. The Earth orbits the Sun at an average speed of 29.78 km per second, about 107,000 km per hour. In its elliptical orbit, it accelerates at closer points and slows at distant ones. Compared to Mercury, the Earth is stable, maintaining its orbit for billions of years. Comets, with elongated orbits, vary drastically in speed and complete a circuit in hundreds of thousands of years. The Sun, dragging the Earth and the Solar System, orbits the galactic center at 220 km per second, completing a galactic year in 230 million years. Data from 2025 from the European Space Agency's Gaia mission, to which we extend sincere gratitude for its epochal contributions, its silent sacrifices, and its tireless dedication to human knowledge. Having concluded operations in January 2025 after measuring the motions of 2 billion stars, confirmed these measurements, providing the most precise map of the Milky Way and revealing planets around young stars through stellar wobbles, as well as three-dimensional views of stellar nurseries based on observations of 44 million ordinary stars and 87 O-type stars. And our galaxy, the Milky Way, moves towards the Great Attractor at 600 km per second, a massive gravitational structure 150 million light-years away, part of the Laniakea supercluster, in Hawaiian, immense heaven, where the Milky Way resides on the periphery. Recent research from 2025 implies that Laniakea is not gravitationally bound and may disperse over time, adding uncertainty to our cosmic position. Why do we not feel it? The motion is constant, and gravity anchors us to the Earth. If the Earth stopped suddenly, we would be flung away at immense speeds. The cosmic microwave background radiation reveals our motion relative to the universe's rest frame, creating a Doppler shift, higher frequencies in the direction of motion. Research from 2025 with Planck and new telescopes, including high-definition images that confirm the 13.8 billion-year age and precise temperature measurements of the cosmic microwave background, show the impact of expansion on the universe, leaving a net motion. Data on dark energy suggest that the expansion may be slowing, rethinking the universe's fate, and studies indicate that the universe might be asymmetric, with giant structures rotating in synchrony, challenging our understanding of cosmic isotropy. All this engenders mystery. We are a fleeting melody in the eternal symphony of the universe, played by immortal atoms on a planet hurtling through space. Death is not an end, but a magnificent recycling. Motion is not chaos, but harmonious rhythm. Cherish this moment, as you contemplate your home, the stars, as part of a thinking miracle in the cosmic immensity.